Let's be real, AI is no longer just stuck in a box. It's not just writing emails or poetry anymore. It's starting to use tools to interact with the real world, and yeah, even to write and run its own code. Now, that's incredibly powerful, but it also opens up a huge can of worms when it comes to safety, a challenge we're going to unpack right now. So here's the billion-dollar question. When an AI can whip up a Python script on the fly, analyze the output, and then use that to decide its next move, how in the world do you guarantee it won't do something unpredictable or even dangerous? How do you build a safety harness for something that powerful? That's what we're tackling today. In this explainer, we're going to break down a really fascinating new approach to this problem. First, we'll set the stage with the AI safety dilemma. Then, we'll introduce a new framework called CAST. We'll look under the hood at its safety gate, see how it performs in the real world, and finally, talk about what it all means for the future of AI safety. All right, so let's dive right in with the problem itself. The second you give an AI access to external tools, all of our old safety playbooks pretty much go out the window. Think about what this slide is saying for a second. An AI writes some code, a tool runs it. The result of that code then feeds directly back into the AI's next thought process. You've just created this wild feedback loop. It's an adaptive, self-influencing system that becomes incredibly hard to predict or control. And this is where the rubber really meets the road. See, in the old days of AI, we mostly dealt with data that was predictable. Each piece of data was independent of the others. But with these new tool-using AIs, we're in a whole new ballgame. We're dealing with adaptive data streams where every single action influences what comes next. All the old statistical rules just don't apply anymore. So if you've got a fundamentally new kind of problem, you're going to need a fundamentally new way of thinking. And that's where this framework called Certifiable AI Safety Theory, or CAST, enters the picture. And this right here is the big idea, a total paradigm shift. The old way of doing safety was like being a food taster. You check one specific action after the fact to see if it's bad. The CAST approach, it's like auditing the entire kitchen. You check the recipes, the ingredients, the whole process to get a mathematical guarantee that a bad dish can never even be made. It's not about checking one output. It's about certifying the AI's entire range of possible next moves before any of them happen. The heart of this whole thing is a concept called the safe set. Now, you can think of this as a pre-approved safe zone or a menu of acceptable behaviors for the AI. It's a rulebook, but it's written in pure math. As long as the AI's cloud of possible next actions stays entirely inside this well-defined boundary, we know we're in the clear. Okay, so that's the big picture concept. Now we're going to get into the nitty-gritty of how this machine actually works. And by the way, if you're finding this kind of breakdown of a complex topic helpful, this is probably a good time to hit that subscribe button so you don't miss what's coming next. So it's cool to have this mathematical safe set, but how do you actually enforce it on a live system, in real time? Well, that's the job of the CAST safety gate. It's actually a really elegant three-step dance. First, the AI doesn't just propose one action. It proposes a whole probability distribution over all its possible next moves. Then, a monitor acts like a bouncer, checking if that entire distribution is inside our safe set club. And finally, based on that check, it makes a decision. And there are only 3 ways this can go. First, certify. Everything looks good, the proposal is safe. Green light. Second, project. This one's really clever. The proposal is maybe a little bit outside the safe zone. Instead of just slamming the door, the system can mathematically nudge it back to the closest possible safe action. It's like a gentle course correction. And third, fallback. The proposal is way off, too risky, and can't be easily fixed. In that case, the system defaults to a guaranteed safe action, like just doing nothing. It fails safe. This visual right here really helps it all click. You can see that red cross, that's the AI's unsafe proposal. It's clearly outside the green safe set. But look what happens. The system doesn't just block it. That blue arrow shows it calculating the mathematically nearest safe point on the edge of that green zone and then pushing the action there. It's a repair, not just a rejection. It's a really powerful idea. We think visuals like that one are absolutely key to making sense of these complex ideas. If you appreciate this clear, visual-first approach to research, do us a favor and take a quick second to subscribe. It really does help. Okay, so the theory sounds really solid, but what makes it practical? Let's take a look at how CAST actually gets put to work and why it's so robust. The secret weapon here is its monitoring system. It's called anytime valid, which is just a technical way of saying it's built specifically for those messy adaptive data streams we talked about. It means you could check the AI after 10 steps or 10,000 steps. It doesn't matter. The safety guarantee you get at the exact moment you hit pause is still mathematically sound. And here's another huge advantage. CAST is brilliant at preventing death by 1,000 cuts. You know, a single tiny risk might seem fine, but what about 1,000 of them in a row? As you can see on the left, lots of tiny risks can stack up and cause a major failure. CAST avoids this with something called global risk budgeting. It basically gives the AI a total risk allowance for its entire operation, making sure all those little risks never add up to a catastrophe. So let's make this super concrete. Imagine an AI that's predicting stocks. It's using a Python tool to check market volatility. Well, its safe set could be defined to forbid any trade that looks even a little bit like market manipulation. If the AI proposes something that breaks that rule, what's the fallback? It's not a system crash. It's a simple, predefined safe action like do not trade. That's a finance-grade safety guarantee. So, no question, CAST is incredibly powerful, but it's also really important to be clear-eyed about its limits and what it means for the bigger picture of AI safety. So let's just quickly recap the big wins here. You get provable mathematical guarantees, not just wishy-washy rules. It's built from the ground up for the complex AIs we have today. It always fails in a safe way, and crucially, the safety check is fast enough to actually run in real time without slowing everything down. But, and this is a really important but, there's no such thing as a free lunch. The creators of CAST are very upfront about something called the verification trilemma. Basically, you can't have it all. You can't have a system that can understand any safety rule you dream up, that can guarantee it catches every single violation, and is also simple and fast enough to actually work. CAST makes a deliberate choice. It focuses on provable, decidable guarantees for the safety rules that we can explicitly define. Understanding these kinds of fundamental trade-offs is, well, it's everything if we want to build a future with AI that we can trust. And if you value these kinds of clear, structured explainers, you can help us keep making them by hitting that subscribe button. You know, this whole thing is summed up perfectly by this quote from the paper itself. The goal of CAST isn't to create zero risk. That's impossible. The goal is to take that scary, unknown, potentially infinite, unbounded tail risk and convert it into something we can actually understand, a quantified, auditable, measurable amount of risk that we can decide if we're willing to live with. And all of this leaves us with a final, really important question to chew on. As these AI systems get woven deeper into the fabric of our society, from our financial markets to scientific discovery, are these kinds of rigorous mathematical proofs the only real path forward to building an AI we can truly trust?